Recording again. Okay, so in this new topic, we're gonna first talk about computational computation graph and then neural network. So the neural network model here we introduce are the basic, very basic shallow neural network. So we'll start from the very basic units called the neuron, but we'll use the tool, the so-called computation graph, to help define the computation process that are needed in the basic neuron units. Okay, and this concept of computation graph is quite important because everything we have, all the computation that happens in the modern machine learning framework, they are executed under a overall control of all the variables. So in this computation graph, all the parameters are defined, all the vector or matrix computation happens here, and all the gradients are also computed within this graph. Okay, so it's a very from the perspective of engineering side, it's a very clearly defined, and it's a very modularized way of thinking of the machine learning process. Okay. So what it is, let's talk about, first look at what is it, okay? So it's a way to understand, to conceptualize, or to visualize machine learning models, okay? So we can use a very simple arithmetic computation as an example. Say we have some outcome function to compute, which is the j of a and b and c. And a and b and c are the three inputs we will use. Okay, and this is a very simple arithmetic that computes 2 times the results of a times b first and then plus c. So it's basically 3 arithmetic operations we have. We first have a times b, right? And then we use the results of a times b to plus c, okay? And we use that result to multiply with the constant 2, okay? So with these 3 separate steps, if we want to visualize it in the computation graph, we need to use some intermediate variables to store the results in the middle. Okay, so we use u as an intermediate variable to represent the result of a times b, and another variable v to indicate the summation of u plus c. Okay, so that's what we have for the first step, which is a times b, right? That's the first graph we have drawn. So that is this part is what we called a computation graph. But so far we know it is a subgraph. The complete graph for the task is not done yet. Okay. So with the intermediate variable, we need to combine it with c, right? That's how we get v from u and c. And we have one more step to multiply the results of v with 2. And that is how we compute the j here. Okay, so now you can see that within each rectangle here, we defined the basic arithmetic operation that happens within that step. So within the step here, it's 2 times something. Within the step here, it's u plus c. It's the plus between the 2 inputs. And here it is a product between the 2 inputs. Okay, so with this graph, we can do very simple computations step by step. Okay, so say with the inputs example 3, 2, and 5, we can compute u, which is 6. Okay, and we plus 6 with 5, which is 11, and then we use 2 times 11, which gives us 22. Okay, that's a very typical forward computation. Okay, which by forward we mean we are starting from the inputs and we want to get the outputs. Okay, all right, so it looks pretty simple, right? And the next we're gonna use the computation graph to do some more advanced, to achieve some more advanced function. Right? We want to use it to help answer the question that are more interested to us. For example, we want to know how much the output will be changed if some inputs change a little bit. Okay, we want to know how the changes in the input variables will lead to the outputs, the changes in the outputs. Okay, so that's something we are usually interested with in machine learning problems, right? We want to know which variable is the most important one, or we like to know how much roles that variable is play in determining the final values of the outcome. Okay, so in answering this question, say we want to know how much j will change if the input a changes a little bit. Okay, what we can do is to, in this example, we will change the value of a by a very small amount. Okay, we make a to be 3.1, increase by 0.1. Then we'll observe the results of u, okay, which is the new value of a times 2, which is 6.2. And the result of v becomes 6.2 plus 5, which is 11.2. And then finally, the new results of j is 2.11.2 is 22.5. And then we can compare the results of 22.4 with original value, which is 22, right? So we can find that the changes in j is 0.4, okay? And compared to the changes in a, which is 0.1, okay? If you take that ratio, okay, which is 4, so which basically tells that if with the if the a changes by 1 unit, then the j will change by 4 units. Okay, and that is the usual and very intuitive way to say this is the derivative of the j with respect to a, right? So that is something we can obtain by looking at the how each intermediate variables changes accordingly when a changes a little bit. Okay, so if we formalize the problem, we say the derivative of j with respect to a, okay, is just like what we did before. It's the old value, the new value of j minus the old value of j divided by the change in a. Okay, so that is how we obtain the derivatives of j with respect to a. Then we can think of the problem in a more stepwise style. Okay, we can actually use the chain rules in computing derivatives, which actually let us compute the derivatives in a backward style, step by step. Okay, because we have intermediate variables here, then we can start. So by our goal is to take the derivative of j with respect to alpha. Then in the first step, we can compute the derivative of j with respect to the adjacent variable, which is v, right? To the immediate adjacent variable, which is v. And then the changes in v is here, 0.2, right? So we know that the derivative of j with respect to v is 2. So you can also observe it from the form of j, right? Because j is 2 times v, and if we apply the rule of derivatives, we know that the derivative is 2, is a coefficient here. And next, we take one more step back, and we want to know the derivative of v with respect to u. Okay, and that derivative tells us how much v will change if u changes for one unit, right? So using the intermediate variables here, the derivative of v with respect to u is the change in v, which is 0.2, divided by the change in u, which is 0.2, which is 1. Okay, so this 1 also comes from here, because v is a linear function of u plus c, and the coefficient is 1 here. So of course the derivative is 1. And now the last step is the derivative of u with respect to a. Okay, and in this case we find that it is 2. Okay, so in looking at this particular function here, u equals a times b, when we want to compute the derivative of u with respect to a, we can view the other variable b as a constant. Okay, so we are actually putting the constant value of b here, and the value of it is 2. Okay, so that's why we have 2 here. So we are done with the backward steps, all the backward steps. Now all we need to do is to chain up all the derivatives in each step using the chain rules of the derivatives, right? The derivatives of j with respect to a is the product between these two derivatives, 2 times 1 times 2, which is 4. Okay, so this one is exactly the results here. Okay, so this case or this example may seem trivial because our computation in each block of in each block or in each node within the computation graph is pretty simple. It's just a plus multiply by constants. So it looks like that the backward step is not necessary. Okay, but we'll later see that if the computation is very complex, mathematical computations, very complex expressions, then we can apply these chain rules or use this step-by-step backward style in a really convenient way. It will really be a convenient tool to help to compute the derivatives of the output function with respect to the input functions. Okay. All right, and then we can do the similar computations with respect to the other two variables, which is b, right, and the c. We just follow the different pathways from the output to the input. Okay, so now we have two colors in the arrows. So we'll define some terms here. We call the green flows is the forward path. Okay, and that's the path we need to take to compute the cost function j. And the red arrows is the red paths, and the red paths are the ways, are the paths we need to go along in order to compute the derivatives of the cost function with respect to the intermediate variables and the input variables. Okay. So if we look at the computation graph in a more general way, and say we have a very large computation graph, and if we take just two nodes out and we want to know how the chain rules are applied between these two neighbor nodes, we can basically use a general function f to determine how the future node is computed from the past. Okay, so let's say the ni+1 node is the future node, and the ni node is the past node. So assume that the future is computed by the function f, and also assume that we know the derivatives of the outputs with respect to this future node ni+1. Okay, then how do we compute the derivative of the outputs with respect to ni? Okay, so that's something we want to know about. Okay, so the chain rule of taking derivatives tell us that we can compute the derivative of L with respect to ni by first taking this derivative with respect to the next node, the future node, and multiply it with the derivative of ni+1 with respect to ni. Okay, and this quantity here, let me put it in a different color. This quantity here can be obtained by the derivative of the function, because we know it is f. So if we use the derivative of the function and give the value ni, it is exactly the quantity we need to plug into here. Okay, so that is the general case of how chain rule is applied in a computation graph here. So now we'll use some short notations. So because it's not convenient if we write the derivative of L with respect to some variable, okay? So that is not a convenient writing style. So we'll use d of n, not d of, but the d ni+1. So d followed by the variable name to indicate the derivative, or the derivative of the outputs with respect to that variable. Okay, so we use this one to indicate the d of something to indicate the derivatives. So we have a compact form for all the derivatives. So the derivatives of the outputs with respect to ni can be expressed by here. The derivatives, the functions, the derivative of the function f times the d of ni+1. Okay. So these are the short, compact notations. Okay. So basically, this principle the chain rule tells us that the derivative of one node can be inferred from the derivative of the adjacent node, and the function that connects the two nodes. Okay, that's something that in general applies to the computation graph. Okay, So a bit of practice here. Okay, so if we look at the function, let's look at the graph on the left here. We assume that the function f here is a sigmoid function, right? 1 over 1 plus e to the power of negative z. That is the sigmoid function, right? And once we know, if we know dni plus 1, then how do we know dni? And then we need to use the chain rule here. So we need to know the derivative form for the sigmoid function. Okay, so we already know that in the lecture for the logistic regression, when we take the derivatives of the sigmoid function, right, we know that the derivative of the sigmoid function is the function times 1 minus the function form, like this. Okay, so that's why the dn is this expression times the dni plus 1. Okay, so that's one example. And an example on the right, it's the similar computation we need to take. If the function is like this, okay, you can try it on your paper, and you will find that the derivatives of it is 1 minus f raised to the power of 2, or f squared. Okay, so basically you want to compute dni in such a style. Okay, so the f is so the f is gone, and it becomes the, so okay, so I didn't mention that because the future node ni plus 1 is the f applied to ni. So here the f of ni is replaced by the ni plus 1 here. Okay, and also the f of ni is also replaced by the ni plus 1 here. Okay, so that's how we do the basically the backward computation from the derivative of the future node to the derivative of the past node. Okay, so I think in the next slide we will talk about the computation graph for logistic regression. But I think I'm gonna leave it to the next lecture. And today we have give a start to the computation, to the topic of computation graph. And I hope you can look at, or once the course is, once the lecture is over, you can give a review to the previous few slides from slide 1 to slide 8, because these are the basic knowledge which are the important building blocks for basically all the concepts related in neural networks, because we're using a graph to represent all the computation within the forward path and the backward path of a neural network model.
Hi, Professor.
Yes.
I have a question. So for the computational graph, so what exactly the motivation when we try to use the chain rule to get the each single of the derivative once we can directly calculate that? Is that kind of like the computational efficient or something like that?
Yeah, so that's a good question, because in the example here, within these steps, we don't have additional parameters coming in. For example, if I set a gamma and beta here, then within these two blocks, we have additional parameters gamma and beta. So we would like to know what gamma and beta fits the, if it's a learning process, then we want to learn the gamma and beta. Then by that I mean I want to learn the parameters. What I want to learn the derivatives of J with respect to gamma and beta, right? So that means we will need to use the derivatives in the past in the future node so that we can know the derivatives of the current node, and these derivatives can be passed along from backward to in the backward style, because in each step we may have different variables to that we want to compute the derivatives with respect to. So this is something I didn't show here in the very beginning, in the most simple example, but especially for large models, for neural network models, we will have multiple layers, and within each layer, we need to compute the derivatives of the outputs with respect to that layer. So that's why we need the computation graph notation. I hope that
Okay.
answered
Okay. Yeah.
your.
Yeah. That makes sense a little bit first. Yeah. Okay.
Yeah,
Thank you.
I hope it will be more clear after the next lecture when we are done with the logistic regression and the neural network, the very basic neuron uh, uh, notation of the using the computation graph. Okay, so if there are no questions, I will stop recording now.